Can you hear me well? Yeah, so I wasn't wise choosing the title of my talk, so I decided to put the entire contents of my talk on the title slide to clarify it. All right, so I think it's obligatory to start the talk with this slide for most talks at this conference. So some of you might be thinking during my talk this. However, maybe the problem is that we're not using enough dimensions in the parameter space, so it should look like that. With this, I would like to thank my collaborators. And someone told me also that a talk won't be good if I don't start it with a punchline. So here's the punchline. The idea is that in quantum info, we like doing quantum computation with Z2 Tori code. And we really like 2 dimensions because it's very practical. And we can do most of the logical gates very easily in a protected way in this, on this kind of platform, apart from one class of them, which are very challenging. And in our work, we make the following observation. We notice that there is an non-trivial topological action in space-time that looks exactly like the missing protected gate. And that observation is actually, like, I hope I will convince you, it's actually quite obvious. And it probably has been obvious for a long time to a lot of people. What's not obvious is to really make it work as a quantum operation that really performs that quantum computation in a protected way. So that's what our work is really about. And now I'm going to try to really systematically explain what I mean by this. So the premise is the following. So we want to have a quantum memory which stores logical qubits which are protected from the environment. In addition to that, we want to do quantum logic, and we want to make sure that if our tools are imperfect, we don't screw up our logical state trying to do that logic. Topological quantum computation is an amazing framework for that because it has this stability, and in addition, it hides our logical observables from the environment because they become locally inaccessible. And there are 2 ways to think about topological quantum computations. One of them is we use ground states, and another one is we use excitations explicitly. And the approach to logical gates in both ways of thinking about it is just slightly different. In one case, we want to explicitly implement the symmetries that just turn different ground states into each other. In another case, we directly manipulate the excitations. And in addition, in that approach on the right-hand side, people usually use more sophisticated non-abelian phases because they want those anyons to have this complicated, like more involved algebra. And in my talk, I'm going to actually focus on this left-hand side computation, but actually some of our findings have implications for the right-hand side, which I'm going to talk about if time permits. And let me just explicate what is meant on the left-hand side with an example of the just vanilla Tori code. So we have this Hamiltonian that is defined by local terms that we can actually measure. And the ground state degeneracy, say on a torus or maybe with open boundary condition, will give us the logical qubit subspace. And then there are symmetries. There are line-like one-form symmetries that actually have 2 sets of Pauli algebra, and that's how we know there are 2 logical qubits on a torus that actually just comes from this algebra. And then there are also global symmetries that, in this case, I'm showing like one corresponding to an automorphism, but with copies of the Tori code of the boundary conditions, we can have actually many of those symmetries, and that covers a large class of gates, and that's very nice for quantum computation. And I will explain just in a bit why these symmetries provide such nice gates. And finally, we can measure these local operators and detect the excitations. And these excitations in the ground state computation is something we want to get rid of. And that's what a quantum error correction does. And we want to actually prove rigorously that that works. And the proofs obviously existed for like 25 years at this point. So, and then when it comes to universal quantum computation, the goal is to be able to approximate any unitary rotation on the logical subspace with a given accuracy. And a very natural object that emerges when talking about bases that generate such universal rotations when it comes to these Z2 Tori codes is the Clifford hierarchy. So that's just a way to classify the basis for the gates that we use to generate these rotations. And so just to give an example, if we have a single logical qubit The first level of Clifford hierarchy is generated by Pauli operators. So these are just Pauli, single qubit Pauli operators. Then the Clifford group is the second level of Clifford hierarchy. That is generated by two additional matrices. These are 2 by 2 matrices. Hadamard is just a Fourier transform. And this S matrix is a diagonal matrix with a phase, which is just square root of Z, basically. We just keep subdividing the phase by 2. And then in the third level of Clifford hierarchy, we have this, we additionally subdivide phase by 2 when we have this additional phase gate. And now we actually lose the group structure as well. So this hierarchy is very, like, it will appear many times in my talk. But the point is that imagine that we are able to do like all the gates up to a Clifford group. Then we can represent the states of a qubit on a Bloch sphere. The north pole is 0, the south pole is 1, and these are the states that are very easy to prepare, again, in a protected way. And then if we only have access to Clifford operations, then the sets of accessible gates to us are these blue states that are related to each other by rotations by 90 degrees on the Bloch sphere. So the number of accessible states, if we only have Clifford gates, is very small. If we want to do universal quantum computation, we would actually want to be able to to get to arbitrarily close to any state in a Bloch sphere. And we are if we only have a Clifford group, we would be very far from that. And then there is a theorem that shows that if you take any other additional rotation that is incommensurate with these 90 degrees rotations, now because this is incommensurate, I can dress it by these additional 90 degrees rotations, and I can get arbitrarily close to any other rotation. And this is an example of adding like just 5 or 4 rotation, which is a T gate, this gated third level of Clifford hierarchy, to get these rotations, and then we can actually go on and cover the Bloch sphere densely, and that's just for 1 qubit. So the point is that these Clifford gates is a very nice group, but they're vastly not enough. And luckily, only 1 more incommensurate rotation is needed in order to complete a universal basis for the universal gate set, and that's what we care about. And then when it comes to multiple logical qubits, of course, there are more gates, but there are not too many that we need to care about. So when it comes to Clifford group, there's just 1 additional qubit, 2 qubit gate that we care about, which is a control Z. So it's a diagonal gate that only gives an trivial phase if both of your qubits are in 1 state. So it gives a -1 phase. And similarly, we care at the third level of Clifford hierarchy. So now these are like those incommensurate rotations that we care about. We have a 3 qubit gate that only gives a -1 phase if all 3 qubits are in 1 state. So these are 2 notable gates because they're going to be important for this talk. So, and then there's one more aspect of universal quantum computation, which is that we want to approximate an arbitrary rotation with an arbitrary accuracy. But not only we want to know how to rotate it using a basis of gates, we also want to be able to guarantee that accuracy if the environment is trying to compromise our operations. So we somehow need to prove a threshold theorem in that case. And this is where things become vastly more complicated immediately. So, so we care about protected gates. So if a gate is, if we can implement a gate using a finite depth circuit, that means that if an environment, say, locally perturbs your system, under a finite depth circuit, this error will spread only a little bit. And actually, we are still able to prove threshold theorems in this case. So finite depth circuit gates are good. They're automatically good for quantum computation. The problem, and actually, if we restrict ourselves to only using copies of 2-dimensional toric codes, as well as maybe putting some boundary conditions and coupling them together, we are actually able to do all Clifford gates on any number of logical qubits. So this is a large number of gates. We would actually need to supplement that only with 1 additional incommensurate rotation in order to get universal gate set, and we would be all set with quantum computation. The problem is that there exists a no-go theorem that says that with such 2-dimensional 2D toric codes, there does not exist a protected way to get that non-Clifford rotation using finite depth circuits. So actually, it's impossible to complete a universal gate set this way. And this means that we will be using, people are using other tricks to complete a universal gate set, and that actually is the bottleneck for protected quantum computation, which makes it so complicated. And yeah, so this is just a reminder that we just need 1 gate. And the way people get this one gate in quantum info, so there are two approaches. One of them is to really go to three-dimensional codes, and in three-dimensional codes, we actually do have gates at third level of Clifford hierarchy. But then there is one more no-go theorem that tells us that there is not a single dimension in which you can get entire universal gate set. So now we need to combine dimensions. We need to work in both 2D and 3D, and we need to switch there and back, and we need to prove threshold, and it does actually work, but it's very inconvenient. And again, working with three-dimensional architectures is clearly less nice than working in 2D. Then another approach to this, which is actually more common and people practically are planning to realize it, like Google really works on that, and there are tentative experiments showing that, is the magic state distillation. But again, this one has a drawback, which is this is an approach that is not specific to topological codes. It's just an approach. It just works for any platform, and it's sort of an engineering solution. It doesn't have like a physics reason why it works. And and then there are some other proposals, but they have their own drawbacks. And the inspiration that we draw an inspiration for our work from these proposals, where sort of you take like a finite depth circuit in 3 dimensions, and then you try to turn that into dynamic computation. The problem is that one of the people who originally worked on this approach, which was Ben Brown, he has remained confused about this approach for a good 5 years before we actually worked on this project. So a lot of things have been unclear, and that inspired our work. And another thing is I would like to shout out to Shenji, who independently came up with a somewhat similar conceptual idea of how to do gates that is also related to going between similar topological phases, except maybe they did not address fault tolerance in their work. But I really recommend checking out this paper. It's pretty cool. And this brings me to our results. So consider a 2-dimensional toric code with boundary conditions such that there is only one non-trivial magnetic operator. Now, this magnetic operator labels the 2 logical qubit states, 0 and 1, and these are in correspondence with cohomology classes. So I labeled them by this variable A. The statement is that we can do that also in space-time. And in space-time, this magnetic operator becomes a membrane. And that is also labeled as a non-trivial cohomology class, but now in space-time. So that's how I'm going to be keeping track of our logical states. And the important parts that went into our work is that for the topological phases that are relevant for our work, we can take their path integral, and there is a systematic method that my collaborator came up with to turn that path integral into a circuit, but not just any circuit, but the one that really extracts the error syndromes and then can be used to do error correction. And that's quite non-trivial. And that was an important part of our work, but I'm not going to really talk about this much here. It's just something to keep in mind. Okay. So now we are going to take a few copies of toric codes, and I'm going to label them by color. These are in 2 dimensions, but now I'm going to try to realize them in space-time. So these are going to be circuits that live in time and kind of arrange things in space. And so, for example, what I can easily do, I can just bring these toric codes in the same space-time region for some amount of time and then bring them back. And then I will be realizing the topological action of the toric code, which is actually just trivial. Alternatively, I could try to, when all my toric codes overlap in one space-time region, I could also try to give it a non-trivial topological action. And these topological actions are actually classified by cohomology operations. So these are sort of operations that respect your ground state space. They might rotate it, but they're respected. And one example of such an operation is a double cup product. And in a dual dual of that is actually just counting the parity of triple intersections between the membranes in space-time. That's what this operation really is. So if we somehow can arrange that there is like an odd parity of triple membrane intersections, then this topological action would give us a -1 phase on a state that has all these 3 membranes. What does this really mean? So notice that my membrane, it just kind of continuously goes in the same copy of the toric codes through space-time. And it only is present if my input toric code was in a logical 1 state. Otherwise, it's just absent, and there cannot be a neutral triple intersection. So to get this -1 phase, I needed to input all 3 copies of the toric code in a one state. That means that whatever the total action the spacetime circuit has achieved is -1 only if all 3 input states are 1. And that's exactly the control Z gate. And then control Z gate is a non-Clifford gate. So this way I should be able to achieve this, this gate. And more formally, what this means is that in a spacetime region where we have multiple copies of the toric code meeting, we want to realize a non-trivial topological phase, and in this case, it's a Digraph-Witten with a type 3 cycle twist. And I hope at this point I made the idea of our approach sound plausible. But if someone might have already noticed that I've been doing something illegal. I've been using an illegal domain wall between toric codes and a twisted quantum double. To show this gate. So in reality, things are much more subtle than what I showed. So what I showed is sort of like wishful thinking. That's what we want to achieve. But in reality, to actually make this work, it requires a little bit more thought to put into it. And for this, I need to talk about 3 aspects of this. First of all, what is really going on in the bulk, in the spacetime bulk of such a protocol? And then what are the allowed domain walls and what are the boundaries? And then once I talked about all these elements, I can combine them together into space-time configurations that actually do work. And this is one of the main results of our work. So let me talk about bulk action. So we will be concerned with toric codes.
Sorry.
As well as,
what's the problem with just working with the twisted quantum double all the time? Do you?
Yes, so the problem is that, so there are several problems. One of them is practical. We really prefer to remain in the toric code phase as much as possible. Because just for, like I will explain it a bit more, but it's much harder to have threshold for non-abelian phases and to have a good threshold especially. But in addition, there's actually not a good way to store qubits in non-abelian phase, in ground states of non-abelian phases. For example, on the torus, copies of toric code have powers of 2 ground state degeneracy. But twisted quantum double has a ground state degeneracy 22. And like, I don't know how to put a discrete number of qubits into that. Yeah.
To explain this picture a little bit better, I'm confused about so this is a space-time picture.
Yeah.
There are 3 torus at the bottom?
So there are 3 patches open, just
3
with
patches.
open boundary conditions. Yeah.
And then it's just 3 square, and then it's inside 3 square cross I.
Sorry?
So the space-time picture is 3 square across the interval.
Well, in the interval is tilted such that they meet, and then I move them over.
Okay, I worry about the assertion this is the intersection number. We have manifold with the boundary.
Yes.
Intersection is pretty tricky.
Yes. Yes, I will take care, like the rest of my talk, I will be taking care precisely of that, exactly. So right now I was a little bit hand-wavy in order to explain sort of what we want to take advantage of. But in reality, we do care about boundaries and we do care about how exactly we arrange things in space-time. And that's the purpose of the rest of my talk, basically. Yeah, right. So, okay, and in the bulk, so the kind of bulk action, so we first of all, we need to write down what the action is in the bulk. It's just a topological action that we can then turn into a circuit. So for the toric codes, it's path integral is just trivial, and we just sum over all closed membrane configurations, which are enforced by stabilizers of the toric codes. And then for copies of the toric code, we just label those membranes. I will label them by colors. And then for the twisted quantum double, we will have membranes that are labeled by 3 colors, but every time there is a triple intersection, there is a -1 phase. So that's really the topological action we will be realizing. Now, so this phase is interesting because it's actually non-abelian, and it is equivalent to untwisted quantum double, the usual KITP quantum double of D4. And this is a very nice model. I'm not going to talk too much about its properties beyond what I already said, but there is a nice bonus that Ruben and Nat helped experimentalists really simulate this modeling experiment. So it's nice enough to be experimentally available. And okay, so now this brings me to the next part, which are domain walls. So the kinds of domain walls we will be interested in, they don't do anything fancy. There are no 2 cycles addressing them. But so what we care about is that if there is a membrane in the toric code, that membrane actually carries the logical states. And we want there to be a domain wall such that the membrane is continuously shared between the twisted quantum double and the toric code, and that's possible. It's also possible if we have two input toric codes and the twisted quantum double. So we can make our logical information go from toric codes to twisted quantum double and back. But that's impossible for a triple of toric codes and twisted quantum double. Such a gap domain wall just doesn't exist. So that's something we just need to avoid in our protocols. So now another aspect is our boundaries. So on the left, I'm showing what boundaries look like from condensation perspective, and on the right, I'm using something that I'm going to actually use throughout the. Yep.
So what do you mean that there is no gap domain wall? I mean, they are both direct with interiors, so they both have gap boundary. You can just combine gap boundary and.
There is no gap domain wall where all three membranes can go.
Oh, okay.
Yeah, sorry. Yeah. You can just have a boundary from perspective of one of the toric codes, right? But from perspective of information, quantum information, we don't want domain walls where you can terminate one of the membranes because these carry the logical state. Okay, and then, so for the boundaries, the way I will be keeping track of boundaries is actually by a subgroup and a Tuka cycle, and all Tuka cycles that will appear in our in the domain, in the boundaries I care about will be trivial, so those I want to write down. So this is just the simplest patch that we're interested in. And sometimes we will also use this domain wall, which is, sometimes we will also use this boundary, which we call the fold boundary. So this one corresponds to having two copies of the toric code, which are labeled red and blue. And on the boundary that is on the right, I actually choose a subgroup, which is a diagonal subgroup, and it forces the magnetic strings of each of the toric codes to meet together at that boundary. And we call it a fold boundary because it can be viewed as just taking two copies of the toric code, it's sort of, one toric code and just folding it along that boundary. And for example, such a boundary configuration actually hosts only one logical qubit. So it's just really like taking one square of the toric code and just folding it over itself. So that's one of the boundaries we're going to use. And then in addition, we're going to use a similar boundary for the twisted quantum double. So, and this is the special boundary where we kind of glue any pair of colored strings that meet at that boundary. And because the twisted quantum double, we have a non-trivial bulk action that also affects the presence of the boundary, also affects the total action because we want the action to remain gauge invariant. And for this, we need to choose a Tuka cycle that, Tuka chain that, a chain that trivializes the bulk action. And the interesting part about it is that there will be sort of like additional phase, the half stream here. So there are additional phase factors that are now actually dividing the phase by 2 appearing because of special domain walls, so special boundaries, sorry. And for all others, for this type of boundary, we actually will have a non-trivial phase factor acting, or non-trivial action on that boundary. But for all other boundaries that we will have in our protocols, we actually will have a trivial additional action. And a similar property occurs whenever we have two boundaries meet at a corner or like at a hinge. And at a hinge, we will actually have also additional action, which sometimes will lead to additional phase. And that's, I'm not going to show that, but that's something that is going to occur. And now we can put it all together to protocols that actually work. So this is the fix of the protocol that I was trying to draw earlier. So this one is now different. So in this yellow part, this is where we realize the twisted quantum double. But now for any domain wall between toric codes and twisted quantum double, we actually have at most 2 toric codes enter there. So we have 2 toric codes enter here and 1 toric code enter here. And that's why kind of this configuration is allowed. And now we have arranged the boundaries of this entire configuration such that if the input state is in all 1 logical states of the toric codes, then there is a non-trivial number, like an odd number of triple intersections. And this actually realizing this as a circuit, the topological path integral of this configuration as a circuit will give us this logical action. So this is one example. Then we can also use this folded example. So we can input a pair of toricos with this folding boundary as an input. So that carries a single logical qubit. And then we can realize the twisted quantum double in the middle, and then again output a single folded toricode. Here, the interesting part is actually coming from the hinge action. So we'll have this twisted quantum double action in this spacetime region, but the intersection coming from the hinge, and the hinge gives this non-trivial phase. And we have a single logical qubit, and if the qubit is 0, there is no non-trivial membrane going through the spacetime, and then there is no action. And if there is an input one state, then we get this phase from the hinge.
Can I ask a question about the picture before, please? So is the domain wall between the toric codes squared, the in and the out are the same?
This one and that one are the same.
Yeah. But if you were to choose these differently, would you be able to generate other gates, or?
So we will.
Because there are many choices.
Yeah, we would be able to dress it with some Clifford operations, but that's not as interesting. Yeah.
And that's
because it's not really the domain wall that is responsible for this non-trivial actions,
it's
but the
interplay between the green, the red, and the blue.
Exactly. It's more like this non-trivial bulk action of the twisted quantum double that you're trying to take advantage of. And here it's actually the way the bulk action behaves at a boundary and a hinge that leads to a non-trivial phase on a single qubit. So that's also quite interesting. And then finally, this one is slightly different because here the boundary conditions are such that once we implement this domain wall between two toric codes and the twisted quantum double by circuit, the circuit actually performs gauging from two copies of the toric code to twisted quantum double. But this gauging occurs by measurements, and there is like a global measurement of the symmetry that we are trying to gauge here. And the symmetry is this like SPT symmetry between two pairs of the toric codes. So we end up measuring the eigenvalue of the symmetry, and that's like measuring the eigenvalue of this operator, and the symmetry corresponds to a Clifford operator. And measuring an eigenvalue of a Clifford operator is actually a useful method for preparing magic states in quantum info. So upon inputting a specific kind of input states, which is all plus state basically, we can prepare magic states this way. So this is like a special type of protocol, so which I'm showing to illustrate that with these kinds of configurations, we don't only get unitary actions on the input states, but we also get projective ones, which is kind of interesting, and that normally does not occur if you use usual symmetries, like finite depth with multiple symmetries to do gates. Okay, and then, so if, in what I was talking before, I think some of those things were obvious to some of the people in the audience. So I don't think, when it comes to fault tolerance, so I don't think the message that I'm going to try to explain here will be obvious to anyone. So this is like a really non-obvious part of our work. As I said before, we care about implementing universal quantum computation with a bounded error in the presence of adversarial environments. We really need to prove that this works for the most general noise. And in this case, since we are implementing our gates by circuits, we need to assume that any circuit's operation can be noisy, and then there can be additional noise deposited by environment into our system as we go. And we need to prove that as this noise happens throughout the entire protocol and the entire space-time, we can still prove the threshold theorem that we can implement the gates with a bounded accuracy. So this is called like a circuit level noise model, but in reality it's just a physically realistic noise model where like we really allow the environment to we really model the environment realistically. And for any model of quantum computation, that's sort of something that needs to be done, but frequently is not, unfortunately. So here we are dealing with the following complications. So we are performing our circuits, and our circuit extracts syndromes, and some of these syndromes correspond to detecting non-abelian excitations. And let's say these excitations are these red crosses. So because anything in a circuit can fail, we can find ourselves in a situation where two of these excitations are real excitation, and one of them is actually a measurement error, because measurements can be faulty, right? So then we can just decide to correct that, and we could accidentally apply a correction string on a wrong leg of this three-point set. And this way we will actually end up extending the error instead of correcting it. And this extension can actually expand the size of the entire system. So correcting things right away when there are measurement errors is something illegal. Okay, so then we could use a different approach. We could just see how people who work with 1 billion topological phases do quantum error correction. And what they actually do, they keep running the circuit, they keep recording measurement syndromes, and they just record them and don't do anything for a really long time. And then much later on, once they have a very large history of space-time measurements and they know everything that ever happens in their entire circuit, then that's when they decide how to make a correction. That works in 1 billion case. Unfortunately, this approach does not work in non-abelian case because you can't just let those anyon word lines live indefinitely in time and then just still prove that the logical state has not changed. So this is an approach that doesn't work in non-abelian cases. So that we can also not do. So instead, we have to change our decoding strategy. So we have to actually act as we go, but we can't just act naively. And this approach is called just-in-time, and it was proposed by Hector Baumann for the first time, but in a different context. And now we understood that this is something that is actually needed to correct some of the non-abelian orders. So what we do is that for the local errors introduced by the environment that includes measurement errors, they actually kind of cluster. They have this clustering property that they cluster into some sort of balls in space-time. And for every such cluster that we detect, we actually wait out for the time proportional to its size, but not for too long, before making a decision. And then we are likely to actually have discovered that our measurement error was a measurement error, because at some point we will stop measuring that syndrome. And we will be able to tell that these were the actual anyons, and these are the actual anyon word lines that we keep measuring. And then we will close that off and we will correct. And what's special about this is that we can really prove a threshold theorem in this case. And the reason is, so this decoder will still sometimes be fooled by the noise, and sometimes will apply incorrect correction string. However, we can show that because of this clustering property of any local noise in space-time, any cluster won't grow too much. And since the clusters remain clusters, there's still sort of non-trivial region in the entire space-time where logical information can go through unchanged. So that's the non-trivial part. Yeah, there were some questions.
Sorry, just a clarification about those 2 points about can't immediately match and can't wait indefinitely. Mm-hmm. Could you just repeat why you can't immediately match? I don't think I followed.
Yeah, so I can't immediately match because in the presence of measurement errors, there are adversarial situations. So imagine that you have like a small, so your noise is local. That means sort of operators that screw up your measurements and that screw up your system and introduce anyons are sort of local. So imagine there is a small anyon string, and somewhere else on the other side of the system, there is a measurement error. And there could be actually many of those that can occur with constant rates. And then you're supposed to make a decision about what to match. And you can't know which one is a measurement error and which one is the actual anyon. There's no way of telling.
So this point would be true even for 1 billion models?
It's true for any circuit.
But then you said that the second point is true for specifically non-abelian error correction.
So this
can't wait indefinitely.
Yeah. So for 1 billion once, if I just wait for a really long time and then I close all of these loops actually have trivial, they don't break, they don't do anything non-trivial. So just the fact that I have these large anyon loops in space-time, it doesn't lead to anything. But in non-abelian case, it's not the case. It's not true anymore. So I can't use this strategy as well. So, but what I can use a strategy where my effect of my noise remains confined in this space-time ball. That works. And that has an important implication for other types of topological quantum computation with non-abelian phases. Because you see, so we saw that for this topological order, we actually needed to do this dynamical adaptive decoding as we went in order to make things work. But this topological order is actually the closest you can have to being a billion. And the reason is because this quantum double is actually nilpotent. So as soon as and it's level 1 nilpotent, meaning as soon as you've used your non-abelian anyons, the leftover becomes a billion. And you're just left to deal with a billion stuff, and a billion stuff is easy to decode. And so that nilpotence is a very important property. And in addition, just the excitations of this model are really well understood in comparison to other ones, because they are like very close to the toric code. They're very closely related to the toric code. So this is the simplest arguably the simplest non-abelian model to decode. And already there we are encountering these complications when considering a realistic, realistic implementation it in real life. Right, so, and then when it comes to implementing other topological orders, there actually do not exist proofs of being able to realize it at a circuit level, which means that like the proof that this can be realized with arbitrary accuracy has not been completed. So we need to come up with the decoding strategies in order to prove that. And that's still an open question. And only now, quantum computation with non-abelian phases has existed for over 20 years, and people have there is a general belief that these are useful for protected quantum computation, but the proof does not exist, and the decoding strategy does not actually exist for most of them. And it took like 20 years to figure out how to do it, even for the simplest nilpotent group. And okay, so the main takeaways of my talk are that we show a method to take advantage of this non-trivial topological action in spacetime to actually write down circuits that manipulates two-dimensional states. And now we do protected universal logic on two-dimensional states purely. And then we also address decoding in these. We show rigorously that the error can be bounded in our universal approach to quantum computation. And this only covers one maybe part of the results in our paper, which is a very large paper. And then there are many open questions, but the ones I would like to highlight is that it looks like there must be some beautiful mathematical structure underlying our ability or inability to do universal quantum computation with topological phases. And it looks like, since we are still learning new things about it, it looks like it hasn't been discovered yet. So there is room for that. And then, in addition, it would be interesting to look at other topological phases and to see if we can do other bases of gates in them. And finally, there's open question that I highlighted that we actually don't know how to decode most of non-abelian topological phases. Yeah, with that said, thank you.
Hi, thanks for the talk. I just wonder, am I right? Your just-in-time decoder is still somewhat non-local, not a strictly local decoder?
It's not local, yes.
So could you comment on which aspect is non-local?
So in order to make a decision, you need to process everything that happened in space-time up to that point in time to make correct decision. So the algorithm that we have, it relies on knowing the entire space-time history.
Okay, up to that time, you mean the entire history? And
yes,
every...
and also in space as well.
Also in space.
Yeah.
Okay,
so just like usual decoding for topological phases.
Okay, thanks.
Actually, now maybe two questions may be related. So you mentioned a few times you have an accuracy threshold. You can prove there's an accuracy threshold for this thing.
Yeah.
Do you have an idea how big it is?
No, it's an analytic proof, so it gives you a very small threshold, like abnormally small.
Okay, so back to your dynamical decoding. So, you have to go all the way to the history to decode. But suppose you just say, for a certain size, I want to fix a certain thickness. Mm-hmm. If your accuracy threshold is big enough, probably that's good enough.
For a constant thickness, I think I can prove it breaks down. So it has to
constant
be thickness.
breakdown, so it has to grow.
It has to, the depth of this memory, it has to scale with the system size, at least logarithmically, for there to be.
Not very good.
Yeah.
Can I ask a question? Thanks for your talk. So maybe I can try to squeeze in two questions. One, early on, you mentioned it's hard to maybe encode qubits in the ground state manifold of the non-abelian state. Mm-hmm. Maybe I missed it, but when you're sliding these through each other, should I think of naively I would think the qubits are temporarily living in the non-abelian space? Yeah. But then does it resolve the earlier question of how to define it?
So in this particular case, with these all open boundary conditions, the ground state degeneracy of the twisted quantum double is also 8.
Okay, perfect. Okay.
But it's just like in general,
Yeah.
it's unclear how to approach this.
Okay, thanks. And the second question, so you discussed this nice fault tolerance. Can you comment on this earlier work by, I think, Paulin and Goffinet, who, like 2017, also doing error correction for these acyclic models? Like, do you feel they solve the question of error correction in that case, or do you feel there's certain caveats you want to?
So I think there is a caveat with measurement errors because, so they're doing phenomenological noise model, assuming that you know where the anyons are. That's as far as I understand their work, because I don't understand it really well. But as far as I understand, they have a phenomenological noise model where you assume there is some distribution of anyons and then you match those. I don't know if that we can show that that works for circuit level noise, but maybe we can. I just would like to say that I would like to understand the work better.
Just to check, so you're saying you're not sure if the work includes faulty measurements? Is that the option?
Yes.
Okay.
Yes.
So, since after some times you exit the non-abelian phase, no, in your protocol, can't you just wait and try to decode the errors afterwards, while you're in the toric code, it's abelian and you like it more, or what's the problem?
Yes. So the problem is that it occurs whenever you have these anyon world lines, and these correspond to non-abelian anyons, and they go for extensive amount of time. So if you wait until your abelian phase and your anyon world lines go in both abelian and non-abelian, there's still non-abelian in the non-abelian phase, and that's bad.
Okay.
So you have to really keep matching whenever you're in non-abelian phase.
So how realistic is this, like to implement this particular D4 double and these kind of interfaces?
Yeah, I mean, in the cold atom or trapped ion platforms, it's very realistic because they've already did simulations with this D4 topological order. So technically, they can do just a few rounds, and technically you could do that. The question is that a good platform for doing quantum computation in general? I don't know yet. And for other platforms, they are highly restrictive, like superconducting platform. It's extremely restrictive platform for how which exactly, like, you know, in lattices you can use and which exactly operations you can use. So there it's much harder to determine what is realistic and what's not. Maybe not.
Is it possible to describe this gate as a pumping of a domain wall over the 3 copies of Tor code? Maybe.
We thought about it for just a bit. It a little bit looks like pumping a domain wall at some point through like 2 copies of if you fold it through 2 copies of D4 and back, but it looks a little bit complicated, so we didn't come up with any nice interpretation. So it's let me think.
Maybe the question goes back to what is pumping on the domain wall?
Yeah, like you create a small loop domain wall inside the patch and then push it up to the boundaries.
And then you contract it back. But the point is just to look at it in space and sort of rearrange your space-time configuration such that it looks like you're going to grow maybe this non-abelian phase and then you shrink it back. And that's like pumping it through.
The space-time picture suggested that it exists.
Yeah. No, we can write it down formally, but then explaining where the gate comes from is a little bit harder.
Related to that question, isn't it a bit different because you have 2 different kinds of domain walls?
Yeah, sure, but that's still, I think it still fits into like a generalized concept of pumping domain wall. Why not? It's more like one of those gates, the one that is like this control Z is, for example, it looks like taking a few copies of the Tor code and then kind of growing this phase and then shrinking it. And that's very similar spiritually to pumping domain walls in general. But this is true that your domain boundary conditions will change as you go, as you do this.
I might have missed this, but how small is the depth for this? Let's say we do a round of a syndrome extraction doing this. What is the depth of this when you actually do a round of this? I assume it's quite low, but...
Actually, it's very low. So if you take circuit realization of 3 copies of the Tor code, there is a circuit that we can write down for the syndrome extraction for the twisted quantum double. that looks exactly like that circuit, plus 2 additional rounds of unitary CCZ gates. So it's just 2 additional rounds of...
I see. So in Fibonacci case, it's actually quite deep, isn't it?
That's true.
Okay. Can I just ask one more question?
Sure.
Why did you prioritize CCZ gates and T gates? Let's say we could have done Toffoli, for example.
Yes, so Toffoli is not something that, it's just not something that naturally occurs. Like it's just not something that is easy to obtain. Yeah, that's a good question. Like CCZ is actually an existing protocol that we ended up just sort of understanding and reframing through this, using this non-abelian phase. So it's also a very nice starting point. These are arguably the simplest ones you can write down.
Okay, if there is any more, no more questions, we can thank the speaker again.